Okay, guys, so sorry for the delay. In the end, the cable didn't fit in correctly, so that seems to be the problem. I'm doing live demos, and now like my setup time was completely destroyed, so I probably need like a short setup time in the middle of my talk when I'm doing the first demo, but hopefully then everything works out. So welcome to my talk, Attacking Next Generation Firewalls, Breaking PAN-OS. Before I start with the actual content of my presentation, I have a short introduction slide about me. As I already said, I'm a security researcher working for ERNW Research. I'm mostly concentrating on the areas of application and virtualization security, and recent research concentrated on two different topics: hypervisors on the one hand side, so this is mainly the Xen hypervisor in the last years, and security appliances on the other side. So last year at 44Con, I published some research about the FireEye vulnerabilities, so vulnerabilities in the FireEye malware protection system, which got a bit of media attention. And now I'm going to talk about the Palo Alto next generation firewall. You can also find me on Twitter using this, the nickname on the slides. So today I want to talk about the Palo Alto next generation firewall. And the subtitle of my talk, Breaking PAN-OS, is talking about PAN-OS, which is the software stack that runs on all Palo Alto devices. So basically, it's the combination of operating system and a proprietary software stack. The device I have standing in front of me is a Palo Alto PA500, which is basically the smallest and cheapest device you can buy from them. But it's running the same software stack as all the bigger devices. So even though this is like the only piece of hardware I analyzed, all the vulnerabilities I will present affect all the large enterprises devices as well. And I'm concentrating on attacks against the device itself, so not too much about bypassing antivirus detection and stuff like this. So what kind of features does the Palo Alto firewall support, or why it's a next generation firewall? Basically, in this case, next generation firewall only means it's a firewall with more features. In the case of the Palo Alto device, these more features are stuff like the management interfaces. So you have like a really good-looking, featureful management web interface you can use in your browser. You can use to configure the device. You have classic shell access, which gives you a restricted command line interface similar to most Cisco devices. You have a lot of features around signature matching. So they have an intrusion prevention system. They can do exploit detection. They even have wildfire malware analysis, which is basically a dynamic execution of malware and analyzing it, which is executed completely in the cloud. They have App ID, which gives you the possibility to filter based on the applications itself. So you can filter HTTP traffic, or you can filter accesses to Facebook, for example. They have a very interesting feature called user ID, which allows you to do firewall filtering based on active user sessions. So you can search for, or you can filter based on your active user sessions inside an Active Directory environment, for example. We look into user ID in depth later in the presentation. And I have a VPN functionality called GlobalProtect, which is basically a combination of different kind of VPN solutions with added features for mobile devices. So of course, I didn't look at all of these features. I mostly concentrated, or this presentation mostly concentrates on the management interfaces on the one hand side, user ID, as well as GlobalProtect. So we look at the management interfaces, what kind of attack surface they give us. We look at the user ID feature, and we look at GlobalProtect. Of course, the management interfaces are kind of an easy target. They are not that interesting in the real-world environment because normally you shouldn't be able to talk to the management interfaces in like a hardened environment. So even if you find a bug in the management interface, a normal attacker in an untrusted area of the network should probably not be able to talk to these interfaces. User ID is more interesting because normally you have like untrusted office networks where the user ID functionality is accessible to an attacker. And of course, a GlobalProtect VPN, if you use it as a remote VPN, it will be accessible completely from the internet. So this makes it a really interesting attack surface for us. So the agenda of this talk basically is we are breaking in. As for all these devices, normally you don't get like a full system shell or full root shell directly on the device if you buy it or if you use it as an administrator. So the first step is basically performing a jailbreak of the device. So we assume we are a normal administrator of the device, but we want to get full access to the operating system. Then we'll be talking about the PANOS architecture. So when we have full operating system access, we can look at the actual architecture, what software or hardware stack is running on the device. And then we walk through the attack surface I just mentioned. So we look at the management interface, the user ID feature, and the GlobalProtect feature at the end. And then at the final end of the presentation, I'll have a short conclusion. So let's talk about breaking in. The idea is you have an administrative interface, so you have a command line interface over SSH. You can see like the functionality offered by that on the left-hand side, and you have this web interface. But these interfaces are kind of restricted, so you don't get full access to the operating system. And of course, we need that to find the more juicy bugs in the different components like the GlobalProtect VPN. So the first vulnerability I discovered is kind of easy. You look at the command line interface, and the command line interface is a really restricted interface that can be used for configuration and troubleshooting. But it mostly works by using small command line wrappers or wrappers around standard Linux utilities. So basically, if you call this test SCP server connection command, what happens on the underlying operating system is that the normal SCP Linux utility is called, and the arguments you pass in the Palo Alto shell interface will be passed down to this SCP command. In most cases, they correctly escape everything you can probably think about, like you can't use backticks or a pipe or something to inject like arbitrary commands. But in the case of this test SCP server connection command, they basically forgot to escape the hostname parameter correctly. So what we do here is we inject an option to SSH or to SCP. So we use this -o option command line parameter where we can define a proxy command. And when we then execute this test SCP server connection command, what really will happen is that we move our shell, so the shell of the ERNW user, from this restricted command line interface to the bin bash user. So this allows us, or this gives us the possibility to later on just log in using SSH again and just jump right into a full-featured shell. So this is kind of a nice vulnerability for us. When we have this, we have a normal bash shell running, then we can start looking into the operating system or into the device itself. And so the basic architecture is quite simple. In this case, it's a Linux system. It's running on the MIPS64 processor. The processor actually is a Cavium Octeon Plus processor, which will become much more interesting when we go into binary exploitation in the GlobalProtect chapter. And like the device I looked at actually runs the PANOS 6 something version, which is kind of old. So this one is actually still using a 2.6 kernel version. Palo Alto also offers this as a virtual appliance, which is interesting because, of course, the virtual appliance doesn't run on MIPS, it's running on x64. So the whole software stack, the whole PANOS architecture has kind of support for multiple different architectures. If you look at how they do like the basic firewall stuff, so like the basic filtering, nutting, and what you can imagine, it's all implemented on top of standard Linux capabilities, so of the standard Linux network stack, which is, from a security perspective, is actually kind of a good idea because the Linux stack is really battle hardened, so it doesn't have any trivial bugs, so you won't find anything too horrible in there. Of course, they offer a lot of features that can't be found in a normal Linux system, and everything, or all these features are implemented as proprietary Linux user space processes that are just running on the operating system. So a really simplified visualization how this actually looks like. So the system has a standard Linux kernel running on the bottom, and you have a normal GNU user space stack, as well as, for example, the OpenSSH process that's responsible for the command line web interface. But then in parallel to that, you have the Palo Alto software stack. And there are like 4 core services you use, or daemons you use as a core for the communication of the other components. For example, you have this auth daemon, which is the authentication daemon. It's responsible for all the authentication in the whole system, be it a login to the management interface or a login to like the command line interface, or even a login to the VPN. You have the crypto daemon, for example, which has support for hardware security modules. So if your device has support for hardware security modules, you can like outsource all the cryptographic operations to the hardware. And then you have like masterd, which is a process watchdog more or less, and sysd, which is responsible for the internal IPC communication. And then the actual functionality is implemented using these services on the top. There's a process for the user ID service. You have processes for the GlobalProtect and captive portal engine, and a lot more. What's already really interesting, or what you can see, is one core component of this architecture is a web server called AppWeb3 and the PHP interpreter. And we will see throughout the presentation that this is kind of a security critical decision or offers us many possibilities for exploitation. So all web interfaces on this device are implemented on top of this web server. And it looks like originally the whole functionality was implemented as normal PHP scripts, but probably for performance reasons, they moved from writing normal PHP code to writing all the functionality as native PHP extensions, and then only have really small PHP wrapper scripts that call into these extensions. It's kind of an interesting design decision because you have like MIPS64 running PHP native extensions, and it's very interesting for us because this means that you have a lot of native code you can talk to over these web interfaces. So you're not talking to another scripting language or something, you're talking to native code, so you can look at for all the typical memory corruption bugs like buffer overflows and stuff. Now you might ask, yeah, but web interfaces, how many web interfaces does this box have? Or does this implement any interesting features as a web interface? And yeah, that's the case. Mainly, of course, the management web interface is implemented on top of this, but also the whole GlobalProtect, so the VPN stack, is implemented on top of this layer. So this means we have an SSL VPN you can reach over the internet, which is implemented as a native PHP extension. So this is like looking really interesting for an attacker. And they have the captive portal, which is a part of the user ID feature, which is also implemented on top of this. So when we're looking at the attack surface, I already mentioned that, we have the management interfaces, hopefully on isolated interfaces. We have the content app user ID features, which might be reachable from untrusted network segments. And then we have the GlobalProtect, which in many cases is reachable from the internet. So we just walked through that from top to bottom. So let's look at the management web interface. So they have a web UI for manual management and also a REST API, which is kind of cool because you can use it for like automated management of all the devices in your environment. It's implemented on top of this network stack or this AppWeb3 plus PHP stack. And the management web interface itself, so the user interface, has a really large attack surface, but most of it is hidden behind or protected by the initial authentication. So as a normal attacker, even if you have access to like this interface, you can't do too much with the web UI because you don't have like administrative access to the device. However, there's some kind of functionality that you can trigger unauthenticated. And one of them is like the initial parts of the REST API. So basically, you just send a request, an HTTP request, to the device on like the SSL port and request the /API URL, and then you are reaching all the code that's responsible for the REST API. And if you send a post request to this URL, you will find out that this triggers a native function. It's called API wget filter function. This happens before any authentication happens, so this is unauthenticated. And the interesting thing, if you look at this code, if the request, so the HTTP request you sent over there contains the string client equals wget, then they use curl, so the curl command line utility, to invoke an authentication check against an internal web service, so a service that's only reachable over the localhost interface. And the fun part about that is this curl command uses some user-supplied input parameters. So they basically generate like a dynamic invocation to curl, talking to this local service. So you can use this to influence the command a bit. The three main parameters they use are the key request parameter, so it's just a get or post parameter. Possible HTTP authentication headers if you send them, and the remote IP. And what's interesting about the remote IP is that they not only look at the IP coming out of the TCP IP stack, so like your normal IP client connection. Instead, they also use the X-real IP header, the HTTP header, if that's available in the request. And as you can imagine, that's cool because the X-real IP or header is completely controlled by an attacker. So you can more or less put arbitrary values in this remote IP feed. Now it's not completely easy because they use escape shell arc to escape all the values you pass to it before they actually put it in a command line. And escape shell arc works like designed. It puts a single quote before and after the value, escapes everything else that could lead to problems, so you don't have like a direct command injection. However, if you look at the code, so this is like a completely pseudocode representation. It doesn't have to do anything with the original source code, but it's like the same functionality. How this function actually escapes the stuff, you can see if you have this key parameter in the URL, they execute escape shell arc with the destination, the maximum length of the escape value, and the key parameter. If that doesn't work, they abort the connection. They do the same for the basic out header, escaping if that doesn't work. So if escape shell arc returns a value smaller than 0, they abort the connection. Now, interestingly, they also escape this HTTP X-real IP header in this line, but I never check for the return value. So as you can see, you have this if condition. If the escape shell arc function fails, we abort the connection, but I forget this check of the return value when escaping the real IP header. So how can we exploit this? And the interesting part, if you go back and look at the second parameter, it's like the size of this destination buffer where they want to copy the value in. And the function will fail if the input value is so large that the output buffer is not big enough to contain the whole escaped value. And what happens is they still start to write the escaped value into this output buffer. So they start with a single quote, then your content comes, but they don't have enough space for the final single quote, and instead the function fails. But because this failure isn't correctly checked by the code, you have like an off by one in quoting, which allows you really simple command injection. So basically you just send like a really long X-real IP header value, and then you can just use something like this as a key parameter. Because the single quotes are off by one, you'd get a direct command injection. So now I want to do the demo. I have to set up for like 2 minutes, so bear with me for that. At least I hope it will work. Okay, let's see. So it basically just opens like a reverse connection to my system. So I just open like a listener, a netcat on port 1, 2, 3, 4. And on the left-hand side, I just start my exploit. It's going against, so this is like a live demo, so it's a bit complex, but this one is like the box I'm currently attacking. And 1.1 IP address is the internal management interface. So every time you see the 1.1, it's the internal interface. Later on, we will attack the 2.1, which is like an external interface. So if I just enter my exploit, you can see I get a reverse connection from the interface, and if I look, I'm having a nobody shell running on this Palo Alto appliance. So it's a Palo Alto 500 running this MIPS 64 operating system. So you might wonder, this is still a nobody command injection, so it's not that critical, but at the end I'll show you we have a local privilege escalation as well, so we get a root shell out of that. So if you look at the actual request, so it's not a terrible complex exploit, you just send like this post request, the key parameter contains like the URL encoded comment injection, and our xreal IP header is just like an overlong string of A's. And then it's completely irrelevant what kind of data you put in there. So this is an interesting first result. It means we have an unauthenticated comment execution against the management web interface. It's 100% stable. But of course, it's in a hardened environment, you won't be able to reach the management interface, so it's not like the game over already. So let's look at user ID. User ID is a core selling point of all the Palo Alto devices because it's a really cool feature you want to have as a network administrator. Basically, it allows you to implement your firewall policies not on kind of IP ranges or IP addresses. Instead, you can implement them based on user accounts. So you can define a rule like, yeah, the user Bob at my corporation can connect to my domain controller on the RDP port. But user Alice isn't allowed to connect to anything else than the printer or like the web interface or something. Of course, this is cool because if it works correctly, it works for every like environment. So you can, it will work even if Bob is using some kind of Wi-Fi, if he's sitting in the office, or if he's connecting over his remote VPN. So you don't have to work with any IP ranges anymore. Now, how is this actually implemented? So to make this work, the firewall needs an active mapping between IP addresses and active user accounts. And the Palo Alto devices support this mapping in 5 main ways. So you have server monitoring either agentless or with an agent. You have a captive portal. You have client probing. And it's a feature that's also embedded in the GlobalProtect VPN. So we quickly walk through all of those. So server monitoring. The idea is you have agentless monitoring where you just create a dedicated user for accessing the domain controller. So we are talking about an Active Directory environment. So in this case, it would be a dedicated user that can log on into the domain controller. It doesn't have to be a domain administrator, so it can work with like server operator permissions, which is still quite high. But it doesn't have to be an administrator. And then you store the credentials of this user on your Palo Alto appliance. And the firewall uses this user account to connect to the domain controller and read the event logs. And basically, it's just looking for successful logins, and then it can map like an IP address of the successful login to the currently active domain user. You can also implement this for Exchange servers. So instead of using your domain controller, you use like your mail login. And this is kind of simple, but of course it has the problem that it stores your credentials on the device. So if someone pops your device, he will have credentials to a kind of privileged user on the domain controller, which of course can be a problem. So the next step how you could implement this, or what Palo Alto supports, is this so-called user ID agent. And the idea is if you have hundreds of Palo Alto appliances, you don't want that every appliance directly connects to the domain controller. Instead, you have a dedicated agent. The appliance connects to the agent, and the agent connects to the domain controller. now the credentials are stored in this user ID agent, which is just a normal Windows process, so you can install that on every box or any box in your environment. And to accept connections so that the firewall or the appliance can connect to the agent opens up a TCP port 5007 and waits for connections. So we disclosed something in this functionality, so the only thing I want to say about that is you should filter this port. So you should configure it in a way that only the Palo Alto appliance can connect to the user ID agent. Otherwise, of course, you have quite an interesting attack surface if every device in your network can connect directly to the agent. The third way you can implement this user ID feature is the so-called captive portal. And this is an addition or an alternative to server monitoring. And the idea is the appliance looks for connection to port 80 or to port 443 if SSL interception is enabled. And if they see such a connection, they just pop up this captive portal web page and force a manual login. So if your user is just trying to access some kind of internal website, you pop up this login field, and then you have to perform normal authentication to your domain. Again, this is quite interesting because it's also using this app web 3 stuff plus the PHP extensions, so it's an interesting attack surface. Now, but one of the cooler features, or at least I think they're kind of interesting, is client probing. So the problem with this event log approach, so that you connect to the server and ask for the event logs, might be that the event logs are quite old, so they're not like always an actual or current mapping between like the IPs and the clients. They have kind of a high impact on the server resources because you have like a lot of reading of the event logs. And the captive portal is a nice approach, but it only works if you have HTTP traffic and you have like a manual person doing the accesses. So if it's like some kind of automated server connections, then you can't use the captive portal. So what client probing does is you just ask the client, hey, what user is logged in? So I didn't say that's a good idea because as you can imagine, the client, if the client isn't trusted, he can tell you any user ID he wants. And interestingly, this is enabled by default. So it's not like this is a feature you have to enable. By default, every Palo Alto device that has user ID active on this interface will perform client probing against your client if you try to connect to any IP. They implement or they support this implementation over NetBIOS and or VMI. So you can get a NetBIOS connection or a VMI connection from the appliance or from the user agent. So this is both supported. And when I started researching this feature, I found a really interesting blog post by H.D. Moore from Rapid7, where they basically did like an internet-wide scan for their project Sonar. And then they realized, strange, there are a lot of people doing connections to our scanning server. And SMB connections, so they see like, so if you are familiar with SMB in any way, you see password hashes if someone connects to you. So they tried to find out why this is happening, and basically this was a misconfiguration of the user ID feature on a lot of firewalls. So if you activate user ID feature on external interfaces of your firewall will start connecting to hosts on the internet and try to do client probing to find out if they have a valid account in your network. This is, of course, a terrible idea because it leaks like this user account they use for client probing. It's not a classic security vulnerability of the Palo Alto device because it's like a misconfiguration of the administrators, but as it turns out, it seems to be happen quite a lot. So this is a misconfiguration, but as I mentioned, the whole client probing mechanism is kind of suspicious because you can easily bypass it and send like arbitrary values. The setup for this, so to demonstrate you this, I have a short proof of concept. You need an active domain controller and stuff for this to work, so I have a video of this. But the idea is that I trigger a connection attempt, and then I see the client probing mechanism coming back to me, and you should see that I'm able to inject an arbitrary username in this user ID database. And of course, if they do like security critical filtering based on these user ID values, then you have like an interesting attack vector. So how it works is, on the top left hand, I'm logged into the admin panel of the Palo Alto device, and I will just show you the currently active user mappings for my IP. Because I'm a normal attacker, you should not see any user ID mappings here. If the exploit works or the attack works, then you will see a user ID mapping with a value of my choice. On the right-hand side, this is like the script that's doing the actual exploitation, and it's really easily implemented using Core Security's in-packet library. So this just sends like the expected read-by for this client probing mechanism. And on the bottom left, I'll just trigger a connection to an arbitrary IP address and port at the firewall to trigger this connection attempt. And after I triggered the connection attempt, I'm just searching for IP user mappings, and you can see there are no IP user mappings for my IP, so this is the attacker IP. But if you just wait long enough, the NetBIOS client probing will trigger, will connect to my own box, and I'm able to inject an arbitrary user IP mapping. It's also quite interesting because you're not limited to like replying, you can see here I'm like logged on, or now I have a valid user ID mapping for the user Felix at the domain fishbowl.corp. Of course, you could like use arbitrary domains, arbitrary usernames for this attack. You're not even limited to only replying with a single value. So if you know like the user accounts of all the domain administrators in your target company, you just return like a list of all of them and then try to connect to the domain controller or something. And if they do user-based filtering, you will probably just be able to connect to really juicy targets. So the final idea, or the final part where you can use user ID or how you can implement user ID is with the GlobalProtect mechanism. I mentioned GlobalProtect a couple of times before. It's the VPN solution, and it has extra support for mobile devices. You have like desktop clients and mobile apps for every popular platform, so in the end it's just Palo Alto's VPN functionality. Interestingly, after I gave this presentation or after we did this research, some people came to me and also mentioned that GlobalProtect is often heavily used internally, so they don't use it as like an external VPN. Instead, they use it internally to offer this client ID feature. Because if you log into GlobalProtect, you also have created this client user IP mapping without doing client probing or server monitoring or something like this. Now, the cool part about GlobalProtect from a security researcher perspective is that the whole SSL VPN functionality, as well as all the configuration APIs that do like client enumeration and where you can download your client packages and stuff like this, is all implemented on top of this web interface, this app web 3 plus PHP interface. And of course, this is a really interesting attack surface because in this case, it's normally reachable from the internet. And some of the functionality we want to trigger does not require any kind of authentication. And so what kind of vulnerabilities can you find in this interface? So the first thing is it's not like a hardcore critical to find bug or hard to find bug, because basically you just log in. So you try to log in into this SSL VPN and you just send like a really, really long password, like around 60,000 characters should be fine. And you will notice that the server just crashes, so the VPN just dies. The reason for this is that they use unescaped string for XML, so a function directly on this password you pass into there. And this allocates memory, but it doesn't allocate memory on the heap. It uses a locker to allocate the space on the stack. On my small MIPS device, the stack size is quite limited, so you basically just have like a classic stack overrun. You access invalid memory and the box crashes. Depending on what kind of architecture, and if you do this on x64, it might be even exploitable for more than a denial of service, but I have a different bug which is much more interesting to exploit, so we just skip over that and categorize it as a denial of service. The next interesting feature of GlobalProtect is that they have cookies that are encrypted, and the idea is you can have multiple GlobalProtect portals, and if you do a failover or load balancing and go to a different portal, then the GlobalProtect cookies should still work. The problem with this is that they use a device master key as an encryption key. So they do symmetric encryption of the cookies, and the device master key by default is this completely random looking string. By accident, it includes the vendor name. And interestingly, so you can't change this master key, but it's not enforced during installation, and it's actually not documented that they use it for the cookies. So if you look at the documentation, what the master key should do is encrypt your local configuration on your device. And if you're a normal administrator, you probably don't bother with that because, I mean, local configuration on the device doesn't sound too important. The documentation does not mention that this is actually encrypting your cookies. And of course, if you can decrypt and encrypt arbitrary cookies, you have really interesting attacks. We actually didn't implement a full proof of concept for bypassing VPN authentication, because for that you would have need multiple devices, so they are in this failover mode or in this load balancing mode. So I can't demonstrate VPN authentication bypass, but in my opinion this is the case. And interestingly, it's not a security vulnerability, so Palo Alto doesn't seem to think it's a critical security vulnerability. The recommendation is change the device master key. To be fair, if you read the actual hardening guide, they mention you should change it. They don't tell you the reasons. But if you use this, definitely change the device master key, because as far as I know, this isn't changed in the last versions. Now, these are kind of interesting and fun bugs, but the end goal of this whole GlobalProtect stuff is that we want to get unauthenticated an unauthenticated remote compromise of the device. And again, most of the codes you can trigger is hidden behind login functions. So if you don't have any VPN login, you don't have a lot of attack surface to play with. But there's a really interesting function. It's called escape string for XML. And they use this function to escape the username before then sending it as an IPC message. So basically, the whole IPC mechanism of this Pano S works by XML encoded messages. And if you have any XML encoded characters in your username, they have to be encoded or escaped before they are pushed into this IPC message. Now, the function itself does not perform any length checks, so it just escapes the username when you put it in. The destination of this is a stack allocated buffer of size 1024 bytes, which sounds like a trivial overflow. It's not that easy, because before this function is called, they execute a function which is called SSL VPN field filter check user. And this makes sure the username is kind of valid. And by default, it checks that the username, the length of the username is something under 250 characters or something. So normally you are not able to overflow this escape string for XML function, because the check function will protect against that. However, if you look at the actual control flow of this user check function, you will see some interesting behavior. So the idea is, normally you have a username. The username can look something user@corporate domain, so it can be split into two parts, and for every part they execute the bottom code. They do a check if this string contains any ASCII characters, so any valid ASCII characters. If that's the case, they jump to a length check. So this is the length check we want to bypass. If the length is over 250 bytes or something, it's an invalid username. And after that, they do a regular expression looking for certain special characters you also can use. So you're only used to use alphanumeric characters in your username. If this regex check fails, we jump into invalid as well, and then we have a problem. Now, interestingly is this way. We have this function isValid UTF-8, which has kind of a strange naming, because they are looking for a string that contains only valid UTF-8 characters that are not ASCII characters. So basically, they are looking for strings that are completely multi-byte strings. And if that's the case, so if this function returns true, then the length check and the regex check are skipped, which is interesting. Because it turns out that you can trigger this if you just log into your SSL VPN with your username containing a lot of A's, so the A's with dots on top. If you do this, the box crashes again. But in this case, it's a stack-based buffer overflow, so the question is if remote code execution is possible. Funnily enough, this attack is actually easier for German hackers because they have the key already on their keyboard, so they don't need to have any special equipment to exploit this. So now, this is the final main part of the presentation, how we get from this bug that we have to a full remote code execution against this device. The idea, at first, it looks kind of easy. We have a destination buffer, which is a fixed size stack buffer. The binary is compiled without any stack canaries, so they don't use stack cookies, so we can just overflow. We have an executable that isn't position independent. So the app web3 web server binary itself has fixed addresses, so it's not full RSLR. Only the libraries, the heap, and the stack use RSLR. Problem with this binary is that it's extremely small, so it just contains a couple of functions because everything else is handled in shared libraries that have full RSLR enabled. What makes this whole bug quite interesting to exploit is the architecture. It's the first time I ever played around with a MIPS 64 system, which has kind of an interesting properties regarding to this exploitation. So first of all, it's a big endian system, so that means the most significant bytes are at the lowest address in memory, which means we can't do partial overrides. So on x86, if it's a little endian system, we can override the least significant bytes and do RSLR bypasses that way. That's not possible on MIPS 64. Normally, stuff like this isn't needed on MIPS systems because normally you just do a heap spray and jump into your shellcode, because normal MIPS systems, or most MIPS systems I've played with, don't support something like data execution prevention or the NX bit. So normal MIPS processors don't have this feature. However, this KVM Octeon processor of this Palo Alto box supports that feature. On MIPS, it's called execute inhibit, and it just means the heap is not executable. So we can't store a direct shellcode on the heap, which means later on we actually have to perform a full ROP chain on a MIPS 64 system, which turns out to be quite a hassle. Now, the 64-bit part of this architecture is also kind of strange. So if you look at the process itself, it uses all the pointers and the address space itself are still 32 bits. But if you look at the registers, the registers are double the size. So now you have a return address register that's 64 bits wide. This combination is kind of strange. I'm honestly not too sure why that's the case. But as it turns out, this makes code execution a lot harder. So exploiting this, we have a number of problems. The first problem is that our username is not allowed to contain any ASCII characters. So every character in our username has to be some kind of multi-byte UTF-8 encoding, which makes every attack after that more or less impossible. Luckily, we can bypass this by splitting our username into a user and a domain part. The user part is this UTF-8 string of arbitrary length, and our domain part is an alphanumeric ASCII string that's shorter than 250 bytes. So we still don't control this domain part completely. We can't use any special characters, but at least we can use all the alphanumeric ASCII range, which is enough, as we will see later on. Normally, in a stack-based buffer overflow, you would just overwrite the return address. As it turns out, this is not possible with this bug because the return address register is 64-bit long, and because all the valid addresses in this process are in this 32-bit address space, you always have to overwrite the upper half of the return address with zeros. We can't overwrite this with zeros because 0 is not a valid alphanumeric character. And we can't ignore the upper half because these registers are, or the system is big endian. So this means it's impossible to overwrite this return address. luckily, we have something that we can override, and this is a pointer to a PHP context. So the PHP context is like a global data structure or a main data structure used by the PHP interpreter. And this is stored on the stack in the vulnerable function. And it's used before the function returns when PHP body write is called. This context contains pointers to function pointers. So we have like a double indirection we need to bypass. But we can override that with an arbitrary value. The problem with this is that we can't simply point this context pointer to any address we know. Instead, it needs to be an alphanumeric address. So the only solution to actually point the context pointer into a value we control is performing a heap spray. So we can allocate at a known address that's alphanumeric and then point in that location. So the heap spray works by storing up to one. So AppWeb3 has an interesting feature. So this is the HTTP server, and it has an interesting feature you can use for heap sprays. You just store up to 1 megabyte of arbitrary content in a socket connection, and until you send like this double new line that normally would close like the headers, the web server doesn't do anything with this content. So it's just stored on the heap and nothing else happens. And the idea how to exploit this is we just open up many connections, send the payload, keep the connections alive so it doesn't like free the heap memory, and do this like a lot of times. And as it turns out, this works in a way that we reliably allocate our payload at the following address. And it turns out this is actually a valid ASCII alphanumeric string when we convert it. So what do we store inside this heap spray? We can store arbitrary values inside there. So on the left-hand side, this is the disassembly for the PHP body write function. And basically what happens is it loads a function or a pointer from the address that's stored in the A2 register. The A2 register contains the value or the location of our heap spray. Then it loads a value from the A3 register. This just points like in the next offset of our heap spray. Then we control the V1 register, which again points into the next location of our heap spray. And then we see here's a dynamic jump. So this is like the final function pointer in the T9 register. And we put the address of our ROB gadget into the T9 register to get final code execution. And then we can jump into our ROB chain. Now, the problem for full code execution is our heap spray is not executable, so we need a ROB chain. ROBs chains on MIPS64 are kind of terrible because MIPS wants to have aligned instructions, so every instruction needs to be aligned to a 4-bit area. So you don't see any accidental gadgets. So normally on x86 you just jump into the middle of an instruction and you can build arbitrary ROB chains with that. And it gets more ugly because the only object that's at a constant address is this AppWeb3 web server, which only contains 10 functions. So most of them are simply wrapper functions that directly call into the shared library, and all of them are randomized again. So we didn't find a complete ROB chain to get arbitrary code execution just by using a ROB chain, but we discovered a ROB chain that gives us the possibility to create arbitrary files. So the idea is, because we have control over the S1 register and the S4 register, we can load, so this is our first gadget, and we can load a new value into the T9 register, and we can also load a completely controlled value of our choice into the A1 register. And the A1 register is the second argument to the MA start logging function. So we store the address of the MA start logging function in our T9 register, jump to it, and control the second argument. And the function just creates a file at the path stored in the second argument. Now to get a code execution out of this, you need another bug. In this case, we exploited a bug that also contains a local privilege escalation because it's a cron job that just watches for a certain directory and compresses files that it discovers in there. It's implemented as a bash script and contains a nice command injection. So we have we create an arbitrary file, wait for the cron job to execute, and then we get a root shell out of it. I'm already over time due to my late start, so I probably just, I just showed a video of the exploit, otherwise nobody of you gets to get any coffee. So again, I'm having a reverse connection shell opened on the right-hand side, and on the left-hand side, I'm starting my exploit. What happens at first is basically just that we send so this is the heap spray. We are opening a lot of connections, sending data to the web server to store our heap or our data at the address of our choice. We open a lot of connections to make sure this is kind of reliable. So it's not 100% reliable, it's like 50% reliable, which is not too terrible because the web server will just restart again, so you have infinite tries, basically. But of course, it crashes the VPN, which might not be a good idea. And it will crash, because after our rob chain is executed, the web server will just crash. But then we only have to wait until the cron job triggers. In this case, I'm waiting for like a minute to wait for the reverse connection. So when our cron job triggers, it will execute the command injection, and we will get a connection back to our netcat. Normally when I do it live, it gets kind of exciting if the exploit works, because this is the movie, you can probably imagine that it worked. Yeah, you can see over the right-hand side, we get a connection again, and if you use like the uname A, we see we are on the Palo Alto device, and in this case, it's a full remote root compromise. So this is like the worst bug you can have in such a functionality. Thanks. So this is actually it with the interesting or the technical content of the presentation. I have some recommendations. So if you actually use a Palo Alto device, what can you do about that? So all of these bugs were reported to the vendor, they patched it. So on that kind of side, you are pretty safe. However, we still have some recommendations to make these devices more secure in your environment. Of course, isolate the management interfaces. They are very complex, very hard to secure completely. If you use user ID, don't use it for security critical filtering. So you should not protect your management interface using user ID. Because if you then have a vulnerability in user ID, like this client probing stuff, you can again access the management interface and own the box. So in my opinion, it's okay for doing like business-related filtering, so having different departments that shouldn't access certain services, but don't use like your hardcore technical administrative filtering, implement that using user ID. You should definitely disable client probing, isolate the user ID agent, so only the appliance can connect to it, change the master password, otherwise everyone can decrypt your cookies, and of course keep the system updated. In summary, if you have more features in your device, you have a bigger attack surface, which means more vulnerabilities. This will happen for every vendor that implements such functionality. It's just more code will have more bugs. The handling and the response by Palo Alto was very professional, so we are really happy with them. And we also think, even though the vulnerabilities are not that great, the response and how they handled this whole disclosure process shows the right mindset, and therefore we are quite positive about the future progress with these devices. Like from my personal perspective, I find the device itself quite cool. As I said before, if you have more features and you use them, you will have more attack surface. So that's it from my side. Thanks for your attention, and I'm not sure if you have time for questions, but if not, feel free to just come to me after the talk.